Thank you. Yeah, so I'm with OpenOrion, and our goal is to do design optimization end to end. So you take in the specs, you generate the CAD, you automatically mesh it, and then you just generate the CAD and all the fasteners and attachments and everything, just end to end. So the specific task at hand that we're trying to optimize is axial compressors, among other things we're trying to do. And so axial compressors, just in general, they play a pivotal role in jet engines, a lot of energy applications, and just transport of all sorts. And because of that, efficiency is pivotal. And so in the case of jet engines, it can lead to better thrust to weight ratios, noise reductions, and a lot better fuel efficiency. And so what we aim to do in this study is optimize the efficiency of axial compressors using CFD simulations and genetic algorithms. Now, traditional methods use adjoint solvers, and usually the way they work is they deform the mesh. But the problem is a lot of times when you have really drastic stagger angles or really drastic changes to thickness, this can really like deform or skew the mesh a lot, that you can get some pretty big quality degradations, and that can lead to a lot of problems in the simulation. And so the reason why we chose genetic algorithms is, aside from the fact that we're doing our own parameterization at the CAD level, is it's going to allow us to optimize a lot more objectives and also do a lot more zones. So like we can do a lot more stages and kind of factor that as part of the whole system a lot easier, although it will take a lot more iterations. So just a little bit of our methodology. So the first thing we need to do is initialize the blade angles based off of some sort of preliminary setup. And traditionally in turbo machinery design, specifically compressors, this is mean line design. And I'll kind of go into my mean line process in the next step. Then once we get a starting point, we feed these angles into a parameterization. So we have our own that I'll go through. And that will take in those angles we got from mean line and some initial thickness to chord, and then generate an initial parameterization there. Take that parameterization, generate some coordinates, and mesh and smooth that for the simulation. And then once we get a mesh, run that through a simulation, and then use that to get our axial stage efficiency. And then run that iteratively in a loop and converge towards something that is optimal by the optimization process. So yeah, going into a little bit of how we do our initialization. So first thing is like a very common spec you'll see for axial compressors is usually maybe you have a mass flow rate, pressure ratio, what the rotations, operating speeds, or like different inlet conditions for the free stream. And we take all those in and we use mean line design to derive an initial stage thermodynamics for each stage, inlet and outlet. And then from there, you can also derive the mean radius and the just general hub, mean, and tip radii through each stage, which I'll go through in the bigger picture slide. And then from there, you can get those these coefficients for the stage that can let you calculate through kind of first principle fluid mechanics, how you can get those flow angles. And then finally, you can use those flow angles as the initial metal angles for your blade parameterization. Traditionally, they use a lot of things like Johnson method, where you can actually get some deviation or incidence they can add on to your flow angles to get the metal angles. But I figured we're already running a simulation on it. You're already going to get those flow angles anyways as part of the turbo machinery output. So we just started off with the flow angles as the metal angles. So yeah, this is kind of the big picture here. So we have our inlet conditions. We start out with the inlet pressure, inlet temperature. You can use CoolProp to get all the other stuff for the simulation. And then same thing as this inlet density, they're kind of the same. And then this flow area, you pretty much can get through the mass flow rate equation. Pretty much you can solve for cross-sectional flow area. And then from that, you can derive your tip radius, which you can multiply by your hub to tip ratio to get your hub radius. And then from there, you can average these two together, get your mean radius, get your mean blade radius. And then alongside, you have a reaction state rate, which you can get for each stage. Usually people like to kind of start off at like a really high reaction rate, like 0.7, and kind of taper down to 0.5. And then once you, and then you have your flow and stage loading coefficients, which are kind of parameters that you can also derive from your free-stream conditions, and all those go in and calculate your flow angles and your flow velocities, and eventually, and then also you can use free vortex to get like the blade angles at each section, so the mean, the tip, and the hub. And then finally, you get your initial flow angles at all the radii. So yeah, this is pretty much, we just got our flow angles and we're treating those as their metal angles. And there's a lot of blade parameterization things I've seen. There's Parablade, there's NASA's PyTurbo, and they do this very similar concept where essentially you can set up a camber line with your inlet and your outlet angles, and then you can pretty much use B-spline interpolation to kind of connect the camber line part. And then from there, you can start off with an initial thickness to chord. So what I did is I started off with a very common thickness to chord for the max thickness to chord, which is 0.1 at the center. And then these two radii for the leading and the trailing, I started out with 0.05. And started that off as the thickness distribution by multiplying those thickness to chords by the initial chord length. And then finally, so we then get the thickness magnitude, and then we take the normals along the camber line in both the inverse and the direction of the normal, and then we pretty much add those thicknesses up to get our pressure and suction surfaces, and then we, for the leading, the middle, and the trailing, and then we can use those as control points with B-spline interpolation to then get all the points along the blade. So this is our problem setup. So pretty much what we did is I got these camber lines here for both the rotor here and the stator, and I pretty much extended them up plus and minus 1/2 of the spacing, and that pretty much created the two periodic surfaces you see here. So a lot of people also do use the pressure and suction surfaces as well, but what I noticed is there's a lot of instability in the simulation for very drastic stagger angles, so I just stuck with using the camber line instead. And then you have a leading and trailing, which are pretty much your row and stage gaps. And I started out with about 25 and 100% of the chord length, respectively, for the row and stage gaps. And I kept those constant. Originally, I was trying to optimize them, but I noticed that led to a lot of instability. So I kept those constant. And let's see, what am I missing here? So I also used one airfoil for this study. I've seen some other 2D simulation cases where they use multiple airfoils to try to model like the full system. But I tried to keep it simple and also get these simulations running faster, so I just stuck with one. Yeah, so kind of getting into meshing as well. Kind of going back, I forgot to say, so I treated this as the inlet, and then these as the kind of zone between them. So these kind of translate the states between these two zones, and then that's the outlet, and then along here are the periodics for the mesh. And then for the actual refinement, I essentially made the points closer to the airfoil finer, and so I stuck with about 2% of the chord length for those mesh point sizes, and then I stuck with about 2.5 of the chord for the passage mesh sizes. And for the boundary layer, I used this Y plus boundary length equation, and I used this thing called the Schlichting skin friction formula to get the CF value, so I could derive the viscosity for that. And so that's how I had like this very small like first layer length. And then I used a 1.1 ratio to get each successive layer's height from the airfoil. And then afterwards, that went through 2 iterative smoothing operations to get a really smooth mesh. And so yeah, you may be wondering what mesh tool I used. We made our own on top of Gmesh. So a lot of people use ANSYS or Pointwise. I wanted to make something that was very easy to use, very versatile, parametric mostly. And so what you can actually do here is you can just start off with the geometry, and then that geometry gets converted using Open Cascade, and that's then fed into Gmesh as a pointer to Open Cascade. And then what this allows us to do now is we can actually use query selectors on these geometric objects. So you can actually just say, hey, give me those interior edges. It'll select all these edges, and then you can apply all of these operations onto it that are in Gmesh. And then same thing with the exterior. And there's so many query selectors. These query selectors are based on CAD query, which is a library on top of Open Cascade, and there's so many query selectors, like select all the greatest Z edges or the least Z edges. And likewise, we did it for 3D very easily. So we also created a splitting preprocessor, which allowed us to pretty much do a bunch of splits very easily. So that you can establish splits with planes. So essentially we're cutting through with planes. You can actually split along the radius of the ratio along the blade. So over here, we have a 0.5, but the ratio for this wire here, and 0.95 over here. And now it's splitting at these specific angles. So they're splitting outwards, and you can create structure meshes very easily with this splitting preprocessor over here. And then we have a thing that allows us to do automatic transfinite volumes very easily after you've done the splitting, to make sure all your faces are 4 pointers, and then it'll just figure everything else out and then create you a 3D structured mesh. But yeah, for this study though, we stuck with mostly 2D hybrid meshes. And so for our simulation setup, all our free stream conditions we derived from the stage thermodynamic values we got earlier in the mean-line design. And then all the thermodynamic constants I was mentioning earlier was pretty much, we derived them using CoolProp by just taking in the fluid type and then like your inlet, your conditions for your inlet, then you can derive all these other things from that, like gas constant, density, gamma, all that. And then the additional values like the blade translation, static pressure for the marker dials, all that we derived also from mean-line. And then these were some of our simulation setups. One thing to note here is, thanks to Josh, he actually led me to these, but 0.05 was a really good value for turbulence intensity. And then 100 was really good for this turbulence Lambda ratio. So yeah. Yeah, so this was based off of a case I saw, and pretty much they had a pressure ratio of 1.236 and polytropic efficiency theoretically around 90%. And so when we did like our first runs of the simulation, we were actually able to match that very closely. So that was encouraging to see. So we knew our simulations were actually on point with what the actual theoretical values were. And then similarly, all the polytropic efficiency or like stage-to-stage efficiencies were around 83 to 89%. So pretty close. And then the last thing to mention here is that most of the simulations all converged around maybe around 3,000 iterations when it got a really low residual value. So we thought that 3,000 would be pretty good. For a lot of turbo machinery, maybe you want to do around 10,000, but we were going to do a lot of design iterations. So we figured this was good enough to kind of get us going with what designs were good or bad. Yeah, so this is just a little bit about our optimization setup. So we use PyMoon, specifically the NSGA2 solver, and this is known for its ability to do a lot of objectives and constraints, and that's the main thing we wanted it for, because like, you know, Agile maybe like doing multi-objectives is very involved, and so we wanted a framework where you can do a lot of things, not just like fluid flow, but also maybe stress in the future, all kinds of things, thermals. So we chose this because it can handle a lot of objectives. And yeah, the primary objective we were trying to optimize for was the stage-to-stage total efficiency. Yeah, so we were able to get that from SU2's turbo machinery stack. They literally have like all those values for us in the history file. And then the constraints we mainly tried to optimize for were just low residuals and all simulations that converged. And we run this, each optimization for like 1,000 generations. So we noticed around 800 generations, generally it kind of hit its peak for how much it can optimize. And then here is just a little bit of like what we have here for our tolerances. So it starts out with about plus or minus 10 degrees of both the inlet and outlet metal angles, and then it kind of varied between 0.01 and 0.05 thickness to cord, yeah, and then the rest was kind of kept constant. And these are some values that we've seen to work pretty well. Yeah, and so these are some of the results. This is the first iteration directly from the values of mean-line, and started out around 83%, and it went all the way to about 89% efficiency. And that was really encouraging to see because the polytropic efficiency for that case was 90%. So at least at the 2D sim level, it got pretty close, almost 7%. So this is some of our future work here. So the first one is we obviously want to do 3D as part of this. And so that's why we mainly developed a a lot of the 3D capabilities in MeshQL because we wanted to make it really easy to do 3D meshes, completely parametric and automated. And so that was the first thing. And then the second thing is 3D simulations take a lot of time. And so doing a lot of these iterations is obviously, in the short term, not going to be very feasible a lot. So what we were thinking about doing is making ML surrogate models for this. And so what this kind of involves, and this is an example of this at the 2D level, but pretty much you take a bunch of 2D, and eventually what we want to do is 3D mesh cases, and you can actually train different models on it. So this one was a convolutional neural network model we trained on 200,000 airfoils, and we were actually able to completely predict this pressure distribution. And so the process of that is then feeding that back into SU2 via the restart interface as an initial guess, so it'll actually converge a lot faster. And the second thing is we wanted to start incorporating more adjoint methods in as part of the genetic algorithm approach. And so we actually wanted to make the CAD kernel itself auto-differentiable. So actually being able to get the derivatives of the CAD directly from the CAD kernel itself, and then use that as part of adjoint. So yeah, this is the conclusion. Pretty much we're able to enhance the stage-to-stage efficiency pretty well. We were able to reliably generate valid meshes, and that allowed the simulation to converge. Have a broad spectrum of parameters for the blade angles that didn't decline mesh quality, and made the entire system end-to-end, so you can explore a lot of iterations of different designs very fast and efficiently. So yeah, that's it.
Thank you very much. So, we have 3 minutes for questions.
Just a question towards your G-mesh scripting.
Yep.
You said that essentially the point to make structured meshes that you have automated.
Yeah.
For basically hard coded for this kind of channel with a latency, because I always found myself, generating structured meshes is a pain, edge orientation, and
yeah,
it can get super.
Yeah. So right now, obviously, this is a very simple 3D case. We're trying to make it so it'll be automated for multiple, I guess, multiple variations of this. And so you may notice like some things here, like, let's see, I think I have it, snap equals true. So what this will do is like when it actually does some of the splits, based off of some level of tolerance, it'll actually snap to the closest vertices. And then also you have like things like ratios. So it doesn't matter necessarily what your geometry is. It'll take it along some certain amount of ratio along this wire, and then it'll do a normal split and then try to snap with the closest edge. And so we did this so that like parametrically it would try to generate this mesh for like a broad spectrum of different types of like shapes. So that was the approach there to try and solve some of those edge cases.
Yeah, because of course communicating the edges so that you know which edges belong to the same model points.
Yeah.
In the last slide, you showed that you want to use sensitivities.
Yep.
But I did not understand which kind of optimization, because you showed genetic algorithms like derivative field, which now where you use this sensitivities.
Yeah, so the sensitivity we didn't do an adjoint. That's what we're going to do in the future. Right now, it was just principally getting the efficiency directly from the SU2 output, and then just using that as a metric with the genetic algorithm. But what we want to do eventually is incorporate adjoint into this. So this is in progress right now.
Incorporate to what?
Into the optimization level.
You want to switch to gradient-based.
Yeah, so we want to do some sort of hybrid between gradient-based and genetic, because genetic still allows us to do a lot of more objectives, but we want to also do a gradient-based to kind of speed up the iteration cycles. Yep.
Right. If it's super quick. Where do you get this geometry? Do you have experimental data for
Yeah, for this, for like how we generate this ML model here.
general for the compressor?
Oh, the test case.
Yeah.
There was like an online university case that we found, and we just,
All
yeah, it's already been valid. Yep.
right, thank you.
Yep.